in today's class, we're going to start talking about advanced core design. So if you have taken the full theories of course, like if you start with an undergraduate course of digital design, computer organization, computer architecture, then advanced computer architecture. So probably advanced computer architecture should start at this point. Then 5-stage pipeline or single stage, single instruction data path should be the assumption for a regular computer architecture course. And starting from this point, it's more about advanced computer architecture. But since we're already in April and I'm just going to talk very briefly and touch every topic a little bit in today's lecture. So this Thursday, I'm going to talk more on GPU architecture. So it's the GPU core design. Then on next Tuesday, I'm going to move to the memory system, especially talk about the cache design. Then next Thursday and the Tuesday after, we're going to have 2 guest lectures to give 2 lectures to talk about some like the most state-of-the-art research topics that they are working on. One is talking about machine learning systems. The other one is talking about quantum computing. So give you some feeling about something new that is not like when the algorithm we're talking about was 1960s, but research today is 2020 something. So everything changed a lot, and let's see what people are researching in today's research field. Then after that, we're going to come back and we're going to talk about the memory system for GPUs. Then see that's probably close to the end of April and see what we can do. Probably talk more on cache coherency, memory consistency, or the DRAM structure or the network on chip structure. That's for probably we have 1 or 2 lectures that can summarize the whole semester. Okay. So in today's lecture, we're going to continue with the 5-stage pipeline design, and we're going to talk about some more advanced core design topics. And especially today, we're going to focus on dealing with hazard when pipeline cannot go perfectly. Okay, so what is a hazard? So as a starting point, we were talking about 5-stage pipeline. And in a regular 5-stage pipeline, we start with fetch, decode. Decode sometimes is also like people also include the reading the register file, and in some type of design, they also have a read stage, and then execute stage, memory stage, and write back stage. So those are the typical pipeline structure. Now, if we have a perfect execution, like these 3 instructions, then we may be able to execute in this way. So starting from this point, this type of representation will be our standard representation. And because it's going too complex, then it's really hard for me to draw the circuit for you and to reason about what exactly in every cycle, how data flows from one register to another register. Now we're going to go towards a higher level to leave the circuit level, but go to a higher level so that we understand the abstract concept of how things work. So this is a typical pipeline diagram, and on the x-axis we have time, and in the unit of number of cycles, in the y-axis we have the instructions, and see how these instructions relate to each other. Then this is an example. We have this add instruction, sub instruction, or instruction, and AND instruction, and there are some registers they're working on, and we assume that this pipeline works in a perfect way, but you may notice some problem here, right? So what's the problem is actually by this particular time, we write data back, right? And what do we write? We write back S8. Then S8 is available, it's written in the first half of the 5th cycle. Then in the next cycle, in the next instruction, we need to read it. When we need to read it, if we force a pipeline execution, we actually need it in the 3rd cycle, right? We need to decode. Decode is also reading the register. If we take this register, we read from this register, we'll read some garbage data. It's from the previous instructions, and the result we're expecting when we consider program order. So program order means we always execute these instructions line by line as if we're executing one after another. But because of performance optimization, we are actually executing them in some sort of parallel, right? So in that case, there's a problem that this S8 will read some garbage data, then will generate a wrong result eventually S2. And this is something we don't want. And also in the third instruction, we also have this problem that this S8 will get some garbage data because this result is only written at cycle 5, right? Then only at this time we can get a correct result. So at the first half of cycle 5, we write to the register, and at the second half of the cycle 5, we can read from this register, and this end instruction can get a correct result. And this is definitely not okay. We need to guarantee that no matter how we design our microarchitecture, we can still execute the result as if we're executing one instruction after another without breaking the order. Okay, so what can be the solutions? And this is called a hazard, because this is hazard. That hazard is defined as a situation that prevents an instruction pipeline from generating the correct result without interrupting the pipeline execution. So if we still have the perfect pipeline execution, if we have no special treatment, we'll get a wrong result. And this creates a hazard. And what type of hazard that we have? So this is a big category of hazard that we call it a data hazard, because there are data dependencies between the values within the registers. And what can be the data hazard? Then every time people ask me what kind of the data hazard there can be, then I always think these 4 cases. Read after read, read after write, and write after read, and write after write. And only one hazard is not valid, because if you read, no matter how many times from one register, you can still get the right value. So read after read is typically not considered the hazard. But read after write, write after read, and write after write are considered different type of hazard. Okay, and I will require you to tell the different type of hazard according to a program. And for now, we can see this is a particular hazard that is called RAW, read after write, raw hazard. What is a read after write? We try to read this S8 after the previous instruction, write S8, right? So this is a read after write. Then this hazard happens because this write cannot happen fast enough. Now, because it cannot happen fast enough, we cannot really get the correct value at this instruction. Then if there's a hazard, we must take some solutions. So these solutions, we can either use 2 different ways, or 3 different ways. If you are really smart, you can find a way that you don't have complex circuit and you don't sacrifice performance. But this is really hard. Then you may now know the other 2 methods, right? So one method is to make the performance slower. Just come back to the original multi-cycle execution style. Then in multi-cycle execution style, we definitely can go back to the correct execution pattern. And that is sacrificing performance. The second way is to add the circuit, add complexity to make sure that we can solve this problem. Then sometimes the third way may not be even possible, because there are some constraints that you have to really make the decision and really make the right behavior in 1 to 2 cycle time. And 1 to 2 cycle is like 1 to 2 nanosecond, or even smaller than 1 nanosecond. If you say, oh, I want a neural network to solve this problem, it's very, very unlikely, because you don't really have the time, and the overhead of a neural network is too large, too high. So you really need some really, really super simple algorithms and design to make this really works. Okay, so what are the really cheap solutions? So cheap solutions is to add NOP operations, NOP, which is not operations. Not operation is a special opcode, and it's designed to not do anything, but it's just a pipeline filler. So we fill 2 instructions so that we actually delay the start of these sub instructions. Now we add 2 instructions, and these instructions although we're not really doing anything, we still need to go through this pipeline. Then we still need to fetch instruction, decode it, execute it, although no ALU result is selected, no memory is doing anything, no memory action, and no write back, but we still take these 5-stage pipelines. So inserting 2 knob operations, we're postponing the execution of this instruction so that we only execute the decode stage at cycle 5. Then in this case, we can always get the correct result in the third, in this instruction, in the sub instruction. Okay, simple solution, but it works. So what's the advantage and disadvantage? The advantage is really simple. And it's pure software based. So when I say it's pure software based, it's mainly compiler based, right? So if we have a solution that can either modify the software or can modify the hardware, we definitely want to select the option that only modify the software. Why? Because designing some feature in the hardware takes much longer cycle, right? Like more people need to get involved and harder to debug. It takes longer cycle and more likely they can produce some error. And if this feature is built into the hardware, it's much more difficult to change it in the future. If it's in the compiler, well, then it's a problem of GCC 6.3 versus 6.3.1. You just release a patch, you can solve this problem. So if the solution is within the realm of software, it's much easier to change it, and it's much more flexible. So the advantage is actually very simple and is a pure software solution. But it also has disadvantage. What's the disadvantage? It has low performance because we're delaying the execution and we're occupying 2 pipeline stages with instructions that are not doing anything. So those instructions are pure overhead. And another, actually a bigger problem is we're actually mixing architecture with microarchitecture. Why? Because this 5-line pipeline stage is a microarchitecture thing. Then you may design a 6 pipeline stage or 20 pipeline stage or 1 or 2 pipeline stage microarchitecture. Then in this type of thing, if you are suddenly say, oh, I'm changing from a 5 pipeline design to a 20 pipeline stage, you have to modify your design to add 19 knobs, right? I'm just making up this number, but this number of knobs is a microarchitecture thing. But remember, if it's microarchitecture, it should be done by hardware. If it's architecture, it should be done on either side, but it can be done on the software side. So then this software actually have an assumption that we're working on a microarchitecture that is a 5-line stage, and these 5 pipeline stage, and this 5-line pipeline stage are these 5 pipeline stages. Then, so basically we're saying, oh, these 2 knobs requirement are defined by the architecture, not the microarchitecture. So it puts more constraint to the microarchitecture design. If this is the architecture level definition, we basically have no way to define a 20 pipeline stage instruction. If we design a 20-stage pipeline design, then this optimization will not work. Okay, so this problem, this design mixed architecture with microarchitecture and limits the flexibility of designing microarchitectures. So we really want to have a clean minimum architecture design so that we can keep the compiler flexible and both the compiler and the microarchitecture flexible. Okay, so those are the problems of knob. Then just following this idea, if this knob is a microarchitecture concept, can we really do it in a microarchitecture domain? And yes, we can solve it in a pure microarchitecture way and do not let the compiler to get involved. In this case, we want this pattern of execution without a knob in instructions, but we still want this decode to execute at this line of code, right? So what we can do, we can add here, I can add extra decode stage. Then with this, I'm saying there's a decode stage. It's basically say, oh, it tries to decode. Now we detect a problem. We prevent its moving forward. So next cycle is still doing decode. Then if we detect a problem, then in the next cycle, we still let it to decode until this decode is okay, then we really get a safe data that we know, oh, this data is the right data, then we can move on. Now in this case, where sometimes like people will write decode here, sometimes people will write empty box or X here, just say, oh, we're not really doing the useful thing at this stage. Then this can be achieved in the hardware by adding an enable pin to the register. So if we decide, say, oh, we cannot allow it to update, we set enable to false so that this pipeline is not moving forward. In this case, we're actually adding two pipeline bubbles here, two stages that we're not doing anything. Now we're adding two pipeline bubbles, and this is determined only by the hardware. And the microarchitecture determines, oh, we need a bubble here, so we'll delay the execution. Then this is a much better design because it's a pure microarchitecture, and nothing prevents you from like developing a 20 stage pipeline, because your new design just add new bubbles. No matter how many pipeline bubbles that you actually need, you just add them, right? Add in the hardware. Then, but okay, the disadvantage is still the performance is still slow, and is as slow as adding knobs. It's the same performance. We end at the same cycle. Then it requires extra hardware because we really need the hardware detection to say, oh, can we really move forward? Can we really move forward? So at every cycle, every instruction, we need to make this determine that we can move forward or not. So the extra hardware will consume more energy, will consume more energy, and will reduce the die size that's to be used for something more useful. As you can see, starting from this type of design, the design is getting really complex, and where the CPU is actually spend a lot of die size and energy on this type of determine the right execution path, so that it can limit the size that's really for the ALU, the unit that can do the calculation. So GPU is going towards the other direction. It tries to make the pipeline, the control stage, super simple, and so that we can have a lot of stages, to a lot of die size, a major die size dedicated to compute. Okay, so that's the philosophy difference between a CPU design and a GPU design. CPU has complex control, but GPU has simple control, but more die size on the ALU unit that can provide more compute power. Okay, then this is one design. This is a stop pipeline. It's a slightly better design, but can we get an even better design, or going towards the more complex direction and see if we can make it even faster? So we can look at this problem again. Here, we assume that we pass this data through the registers, right? So we write back the register so that we can read from the register. But when exactly we get the result? So actually after the execution stage, at the end of the execution stage, at the end of the cycle 3, we already have the result. And when we need the result of this sub-cycle, we only need it at the beginning of the 4th cycle, right? We produce the result, we generate the result at the end of the 3rd cycle, and we only need to use the result at the beginning of the 4th cycle. So the problem is there's no real conflict, and the conflict comes from the assumption that we only use the register to pass the data around. And that is not very efficient because we need one stage to write back and another stage to read from it. So if we can use something else, if we can directly use a wire to pass from one stage to another stage, then the performance will be much higher, and there's no need to add bubbles in this case. So this design is called value forwarding. So what is value forwarding? Is we add extra wires between pipelines. Once we get, this is an ALU, right? This is an ALU performed execution stage. Then the ALU you can think there's a locking register between these two stages, and right after this register, we can have a through wire that go back from the fourth stage and connect back to the beginning of the ALU. Now, of course, whenever we have more selections, we need more complex multiplexers and the control signals to select which exact data we want to use. Are we going to use the data that is read from this decode stage, or are we going to use data from these through wires, the loop by wires? So more multiplexers and more control signals, and the more complex decode stage and more die size, more energy consumption. But at least if we have a through wire, we can actually connect back, and immediately we have the S8 data and we can directly use it, right? No bubble needed. In this case, it's the same. We need S8, and we can actually have a through wire back from the fifth stage to the third stage. Another wire, more complex multiplexer, more energy consumption, and more control signal. But at least we can directly get this result here, so that we can get the execution. We can just perform the execution without delay. And finally, this we can through registers. We already analyzed this part. There's no problem that we can write here and read from here, and we can get the correct result. So this is the regular path. In this case, we use through wires and through registers. We can say there's actually no real dependencies, and by making the circuit more complex, we can have even higher performance. Then, okay, so what's the advantage of value forwarding is it's really fast, it's pure microarchitecture, and the disadvantage is it's complex, it requires more circuit and more logic, and sometimes in some cases we still need stalls. We still need one cycle stall in this case. But in this particular example, we don't have this problem. Okay, for example, when we need a stall is if the first instruction is a load instruction. If the first instruction is a load instruction, we can only resolve the result after the memory stage. If we can only get the result after the memory stage, then we still need a stall or a no-op here so that we can get this execution result in the fifth cycle. Okay, so in that case, we still need stalls. Okay, so those are three simple methods that can help us reduce raw hazard. Then, in this case, you may ask, how we can get a hazard that related to the start with a W, start with a write. So what are the write after read, and what are the write after write stage? Write after write hazard. Can we even have something like write after write? Now, if there's a write after write, then this write, if there's another write, there's always a certain order, and they always say, oh, this one overrides the previous write. There's no problem, right? So then the quick answer is, if you have a very simple 5-stage pipeline, there's no such problem. There's no write after read worse or WAW write after write. It's impossible to have those hazard. In this type of design, only read after write, the raw hazard can happen. Okay, but we're going to make the pipeline more complex because we want more performance. And so in that case, you will see the hazard, different type of hazard will appear. So this is a problem that say, oh, you originally designed a 5-stage pipeline and you can get a correct result already. Then this will take 3 millimeter square and 1 watt power. Then one day your manager tell you that, oh, we have more budget and we're reducing from 7 nanometer to 3 nanometer. Now we have more transistors that we can use and we save energy. So actually we have more energies than we can use, more energy budget. Then in that case, you need to find a way that can really use the die size budget and to use the energy budget to convert the improved energy and die size budget to higher performance. So how we can do that? And definitely one way is to add more cores. But can we make the single core faster? Because in many cases, you cannot really rely on multiple cores. Some programs are written in a single core, a single thread style. Or sometimes if you're responding to user input, you really want, say, if user click on something, you can get the result really quick. In that case, you really want your single core to run faster than this simple pipeline stage design. So in that case, we want this or core design to be more complex and to get higher performance. So there are generally two directions. We can either make the pipeline deeper or we can make the pipeline wider. Okay, so let's start with deeper pipelines, then which make the hazard even worse. And also the wider pipeline will also make the hazard even worse. Okay, so what are deeper pipelines? Then deeper pipelines because people want to have shorter cycles, faster clock cycles, and more like turning from 1 gigahertz to 3 gigahertz so that it can run faster. Now remember, like a perfect running pipeline is always one IPC, right? One instruction per cycle or one cycle per instruction. Then the shorter cycle means faster throughput, right? Like higher performance. In that case, people always reduce shorter cycles so that we can exploit the instruction level parallelism better. So modern design is typically like 20 to 25 stages. Then sometimes I even see even more stages. Then CPU design can go up to 31 stages. That is, I think the record is a pre-core, like the core is an Intel trademark, right? The pre-core era, like when Intel is pursuing higher and higher clock frequency, is up to 31 stages. Then, but this high number only exists in that year, in like early 2000 something, or 2010 something, or it's very likely to be around 2005 or something. Now after that, they realized, oh, it's impossible to keep going towards higher and higher frequency. They start to go with multi-core design. So today, a typical high-performance core is 20 to 25 stages. And by the way, in today's either phone or your laptop, there are typically two different types of cores. Then there's an efficient core. An efficient core has really small die size and really low energy consumption. So when it's not running some task that is not very performance critical, it will select the efficient core to save battery and save battery and save energy. But when there's a huge, massive workload comes in, it will start to transit to the efficient core. So it will change to the performance core. An efficient core can have like 5 stages, 6 stages. Now may not use the optimization that we'll introduce in the rest of today's lecture, but the efficient core will definitely go towards a super high stage and a super deep pipeline and a super wide pipeline. Okay. There's different ways that we can find different trade-offs to achieve the best performance. So you can see this is an example of an Intel architecture that takes a 16-stage processor design. And Samsung M1, I actually don't really know what is Samsung M1. It's where it is used. Is it used in a laptop or is it used in a phone? I don't know. So there are so many stages that, like even fetch is not the first stage. Fetch, before this, I think it's a branch prediction stage, and so on. There are so many stages and even include L2 data to be part of the stage. So like it's even hard to say how many stages are there in this pipeline, because there are different branches and going through different routes, right? So the number of stages is becoming a blurry concept, like in modern architecture design. So what's the problem of a deeper pipeline stages? Then we start with a 5 pipeline stage. And think this previously we were talking about with value forwarding. This runs perfectly fine and no problem, and there's no need to have bubbles. But what if we add a BEQ? BEQ is a branch, right? So the branch can have taken or not taken options. So it can either go back to somewhere or keep going forward, right? So in this case, if we're still executing a perfect pipeline, we'll execute in this way. But how can we know this instruction can be executed, right? We can only know this instruction, like even the earliest time is at the end of the for cycle, right? The end of the for cycle, then we know it's a branch taken or not taken. Okay, so executing in this way will definitely cause some problem because we're wasting the cycles to execute something that we may not even need it. Okay, so how can we solve this problem? And the quick and easy way to solve this problem, or the efficient core way to solve this problem, is to do this, right? Just move it back and we wait until the result to come back. Now we probably don't need to wait until at this point we can start as early as cycle 4, right? So it enters actual bubbles to consider this branch execution. So in a 5 pipeline stage, it's probably not a big problem. It only adds 2 cycle, 3 cycle, or 4 cycle bubbles. But if you consider that it's a 20 cycle or 30 cycle pipeline, even with some memory access, then this can be a big problem because we're wasting a lot of time. Every cycle matters because this program will be executed again and again, right? It's a small for loop. Then small for loop, there are not a few instructions, or maybe a for loop is only 10 instructions. Then for every 10 instructions, you are wasting 10, you're inserting 10 bubbles in the pipeline. So that's a big penalty for the execution, right? In that case, this is a problem actually caused by deeper pipelines. And this is also called a control hazard. So previously we were talking about WAW, or WAR. We consider those as data hazard. In this case, we call it control hazard. Then there's one more type of hazard that we're not going to explicit right here is structure hazard. That means, let's say, sometimes if we want to calculate sub and end at the same time, but they occupy the same logic. Then if they're occupying the same logic, then we cannot let them to execute at the same time. And this is considered a structure hazard. There are conflict in the hardware resources. But anyway, here we have a control hazard, right? This is a control hazard, and we have to add bubbles so that we can get a correct result. Now, how this problem can be executed, can be solved, is we can just go ahead and execute it, right? We can just move forward and execute it. Probably we make the right guess, right? If we make the right guess, then that's good. We just can continue executing it, no problem, right? So just move forward and as if it's a perfect pipeline and there's no problem. So then in this case, we don't need to add bubbles, and then time saved. Then at this time, branches, so what if we make the wrong speculation? So this is called speculative execution. That means we guess it will be taken or not taken. So we move forward, just assume that we guess it correctly. So what if at this stage, at the end of cycle 4, we realize, oh, we know the branch is taken or branch is not taken. We make the wrong guess. What we do is we stop here and we call it, we squash the pipeline. So for any effect that is already taken, we need to remove it. Now for a 5 pipeline stage, this seems simple because we probably only need a few reset signals to reset a few set of registers. But there are many corner cases. What if you have already written back an instruction, right? Sometimes that can happen when we talk about wider pipelines. What if you have issued a memory request that is going into the memory system? Do you call it back, or do you just wait until it to return and just ignore the return the data, right? And also, because this thing is so complex, And then there's a, you must have heard of the Spectre and the Meltdown vulnerability, right? So what is the Spectre and Meltdown vulnerability? I want to go too deep, but it's basically because we predict it will execute this way. So we issue some instruction into the memory system. It's very likely to be a cache miss at the beginning, right? But it's already issued to the memory system and we cannot call it back. So it will go on to the L2 cache to the memory and bring it to the L1 cache. In this case, if we swap another thread, if we change to another thread, another context, we can actually somehow detect if this cache line is there or not by measuring the time. You can if we know, oh, it returns really quick, no, that cache line is there. It returns really slow, we know the cache line is not there. So this is something called a covered channel. A covered channel means we're using some way to pass data from one thread, one context, one user's application to another user's application. Just think, if I'm running Chrome and typing my password, and there's another bad application is running in the background, can use this method to detect your password. So your operating system and your hardware should have perfect protection so that prevents data flow from one application to another. And in that case, the speculative execution in some corner cases can trigger this problem. And actually, speculative execution was there since 1970s, 1980s. Then in 2020, about 2020, I think it's slightly before that, we realized, oh, there's some security problem there. For 40 years, nobody detected that problem. It's really because this mechanism is super complex and can have so many corner cases that can eventually be exploited by people in a later time. Okay, so this is, you think here squash the pipeline is just reset a few registers, but if you consider the core is getting complex and there are so many corner cases, it's a really complex thing, really complex mechanism, and requires a lot of extra circuit to perform this operation, circuit logic. And well, if you want to add a security patch, then what's the best way to do security patch is to go back to this design, right? That's why patching Meltdown and patching Spectre is actually making the CPUs so much slower, because it's going back to a really bad design and there's really no good ways to patch it. Okay, but here, I think the most important thing to learn is that we squash the pipeline and we kind of roll back if we make the wrong guess. Okay, now we roll back to the cache line, and in this case, we already know the branch is taken. Now we'll go back to label L1 and we start to do fetch again. Okay, now in this case, these 2 cycles are wasted, but in a very deep pipeline, then many instructions are being wasted, right? And so now we talk about speculative execution, and we only talk about speculative execution in the not taken way, right? Just keep moving forward. So which way is more likely to happen? And it really depends on how your compiler is written. Now your compiler may write, say, the BEQ, the conditional branch, at the beginning of your loop, right? So if you are going to jump out of this loop, you jump out. Then only at the end you execute a jump so that you can come back to the original beginning point and BEQ and go back. If it's the condition holds, then we go out of the loop. Another way is to wait until the end of the loop, then do the check, then jump back to the original place. So it's really hard to say which one is more likely to take. It's really a compiler issue. Okay, so in this case, we want some better way to say, oh, if we can predict if it's taken or not taken. If we can predict if it's taken or not taken, we can probably make a better decision. So probably if we know it's a taken, we can directly go back to this F, right? we can directly say, oh, we predicted this line will happen. Then we directly fill the pipeline with this f by fetching this instruction. Okay, so in this case, we actually don't need to know this execution result, because either it's taken or not taken, it's very likely going back to the original place. So if you have executed this instruction, like taken once, you know where it's jumping back. You can store that address somewhere, right? You can store that address in extra microarchitecture level register. So you can directly come with fetching this instruction. So we predict is taken. Now, what is a good branch predictor? Then this is the most ancient way of making a branch predictor. So we basically say, we start with, we assume it's not taken. Okay, we start from this point. Then, if we're currently in this state, then we predict it's not taken. So we'll keep going. But if we get it wrong, we know it's taken. Then we take this route to put it into this taken state. In this taken, we just simply predict taken. Then we go that way. Now, if we predict wrong, we go back the other way. Okay? So because we are very, very likely to be executing in a loop, so very likely that we can get a correct result. Okay? But so think about loop. Then some loops execute 3 to 5 times, but in a real performance critical program, your loop may execute thousands, millions of times. That's really common, right? So in this case, branch prediction is very effective. This 1 bit per PC. What is per PC? Is basically by each branch, conditional branch instruction, we have 1 branch predictor. Okay, so like some branch prediction will predict it to taken, some we predict it's not taken. Then the minor problem with this one is easily interrupted by noise. If it's like, say, it's in some loop, then suddenly for one time it just goes out, then it will go back to a not taken, then it will cause a wrong result. And it's very easily to ping pong back and forth between taken and not taken, so that will not stay stable in one state. So slightly complex, changing from 1 bit to 2 bit state is to make it a 4-state machine. So we start from a weak not taken state. Now if it's not taken, then we go to strong not taken. Then we'll stay here if it's not taken again. So it takes 2 taken. So we know, oh, the pattern changes. If then in that case, we know the pattern changes, we start to go with the taken pattern. So it's more resilient to noises and less likely to get ping pong back and forth between this execution. And this is the classical way and is very productive. And actually, in your designs, there are much more complex branch predictors, and branch predictors can be a career of a whole researcher's whole lifetime, or it can be at least a few PhDs to work on it. It's very normal, so very complex topics. So even today, CPUs, like AMD CPU starts to be the first one to commercialize a neural network-based branch predictor. Although I don't know how they can make the prediction that quick, but they really commercialize it. Before that, if you write, say, in a paper, say, we develop a neural network-based predictor, reviewer will say that's not practical, but see, it's commercialized. Then after that, we write a paper, say, use a neural network-based predictor. They say, okay, it's possible because AMD has proved it's possible. Okay, so we talk about meltdown and Spectre vulnerabilities, and those are rooted in speculative execution and branch prediction. Okay. So that's the problem caused by the deeper pipelines. Then think about this thing. What's the cost of making the pipeline really deep? Then is it worth it or not? Then it's definitely worth it. But it's always it must happen with your constraint in your budget, right? The die size budget and the energy budget. And as the core is designed more and more complex, then you need more and more control signals and control logic to consider different corner cases. Eventually, adding more circuit is actually slowing down, right? So people are not going towards very deep pipelines. Like the deepest pipelines today I see is 25 cycles or something. Then they're going towards a wide pipelines. And wide pipelines are so commonly used that even efficient cores may use some sort of wide pipelines. What is wide pipelines? And typically wide pipelines is a description of this technology called superscalar. Previously, we're talking about the architecture that's called single scalar. When single scalar is we only have one data path, one ALU. So we generate a result, one result per cycle, one instruction per cycle. Superscalar means, we can have multiple ALUs, right? We can have multiple ALUs. Then to execute one program, we may execute two instructions at the same time, so that we can generate two instructions two instructions in one cycle. So we're reducing one CPI to 0.5 CPI, or we're increasing from one IPC to two IPC, right? So two instructions per cycle. Then the more ALUs we have, the more IPCs we can have. Then later on we can calculate what's the GPU's IPC. It's a huge number. Okay, so we really want to execute more than one instructions per clock cycle, right? So in that case, we can put more than one ALUs. Sometimes we put 4 or 5 ALUs. So sometimes we can quickly describe a core to be, say, something like a 6-issue. Six-issue, 25-stage core. Okay, these are typically the most important non-commercial terminology. The commercial terminology is 3 gigahertz. These are commercial terminology. Non-commercial terminologies, you say, we have a 6-issue, 25-stage pipelines. So what is 6-issue? That means we have 6 set of ALUs that we can issue 6 instructions at one cycle. Now also when we talk about issue, that some pipelines may have a dedicated issue stage. In this case, you can consider issue stage right here, right? We get the instruction memory, we get the instruction, then we're issuing 2 instructions into the register file. So this is an implicit issue stage. So sometimes we need to determine if one instruction can be issued or not. Then which instruction can be issued. So it's actually a very complex logic there. So it's an issue stage. Now with an issue stage, we naturally split a CPU core into 2 parts. We say everything before the issue stage to be the front end is basically responsible for loading the instructions into a set of registers, a pool or queue or buffer or something, right? After that, after issue, we call it the back end of the core. So the back end of the core is the part that is taking the task and to calculate the result. So this part is called the back end of the core. And by the way, if issue is a stage, then sometimes decode is before the issue stage, sometimes decode is after the issue stage. So it really depends on the ISA and the microarchitecture design. Okay, so superscalar. What are the superscalar that we can see today? So this is an example of the Apple A14. So A14 is a phone chip, right? How many ALUs are there? ALU, 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 at least 4 ALUs. Still, well, I cannot see it clearly. There are specialized ALU, ALU, MUL, right? And what's this one? BR, okay, this is a branch. This is a branch. and this is load, store, store, load, load. So you can see at most in one cycle how many instructions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I don't know if there's any constraints, but if all of them are working at the same time, 15 instructions can be executed at the same in one cycle. That's a lot of instructions. Then, but they don't do something like ALU unit. They don't have ALU unit for everything, because very, very unlikely they will execute the same type of instructions in like same type of instructions for 15 of them. So what they do is say this one is a branch instruction, right? Only take care of branch instruction. Then you have ALUs. I guess this, oh, by the way, these are integer parts. These are integer parts. These are floating point parts. So we have, these are integer ALUs, and we only have one division unit, and it's dedicated to division operations. It takes a rather large die size, and only these two can calculate multiplication. These are probably adders or shifters. 4 of them can take care of load store unit, and 4 of them can calculate floating point operations. So this is the design. On this side, you can see this is the sum-time M1. Then it takes a slightly simpler design, but there's a branch, there's a ALU, load address, store address, store address, fmac, fadd. Mac is multiply and accumulate. So basically, it can perform multiplication and accumulate in one cycle. So three operands. A multiplied by B plus C, and complete in one cycle time. Okay, so these are the sum-time M1. So superscalar is probably, if you're not designing a toy example, super small example, you're going to design something that is superscalar. Okay, now also, this is a very classic diagram that is a rather early stage x86 Intel design. It's probably the first of few generation of Intel Core design. I cannot really match this code name with their generations. But here you can see there's a store data AGU. It's a load address unit. Integer, floating point add, floating multiplication. Then those are different units. So it's not as wide as Apple chips, but it probably has their own design philosophy there. Okay, so it's very, very common to have superscalar design these days. So what are the opportunities enabled by a superscalar? Just consider this program. Now here we load S7, right? And we calculate S8. There's no conflict in these two instructions. There's no dependency. When there's no dependency, we just go through, then these two can execute at the same time. Now in the next group, two instructions we execute at the same time in parallel, and they go through without any problem. So if we run this type of ideal program, we can actually increase the IPC from 1 to 2, so double the execution. And if a program is defined by the number of instructions, like we need to respond to user input with many instructions, we can reduce the latency by half, so which is a very good thing. But sometimes there's problems. For the previous program, there's no problem. There's no dependency. But if we slightly change it, we can see this type of program. Let's read this program a little bit. So because we need to use this as an example again and again. So here we first load data into S8. Then in next cycle, we need to take S8 then to calculate S9. Then here again, we're actually done with S8, right? So we're reusing S8 for another variable. So we sub T2 with T3 and store into S8, and there's another dependency, then we put S8 there. And then we're starting to calculate something totally irrelevant. Then we get S11, then we eventually store it as the result, using the address of S11 and store it back to S7. Store the value in S7 back to the memory. Okay, so there are some dependencies here. And to support this type of instruction, Then so basically this is a like so consider a single scalar execution. If I have some cars that's running in this way, so for example A1 and A2 are a team and they have to run in this order, but B1 is another totally independent car, so can drive faster. If A1 and A2 are slow cars and if there's only one lane, there's no ways to pass them. But superscalar provides an opportunity to have multiple lanes so that if there are some slow cars in front of it, it can actually go faster, right? In this case, we can actually reorder these instructions in this way. So I will explain to you what's going on here. So in the first cycle, we get this load word, right? We get this load word can definitely execute because we're not executing anything anyway. We check this one, we have a S8 dependency. We check this one, we have a S8 dependency. We cannot do it. Then here we check, we have a S8 dependency again. And here we check, oh, there's no problem, there's no dependency. So we can execute this load and or at the same time, right? Now remember at the beginning we say this load and this AND, because this load has an S8 and this AND also need an S8. So there's a read after write dependency. This is a read after write dependency. And because it's rooted from a load instruction, we cannot immediately execute this one in the next cycle. We have to add a bubble. One cycle stall. Right? We have to add a bubble. So this one can only execute in the third cycle. But in this cycle, we can already execute this one because we say, oh, there's no real dependency. We can do forwarding to get this value, right? Because it's execution stage dependency. So at the second cycle, we'll execute store. In the third cycle, we can execute these two. And there's a write after read. Write after read hazard. So what's going on is this we're writing this S8 result, right? So if we're not taking care of this one properly, we will actually write this S8 before we're reading this S8. Although in this order, there's no problem. But if we're not doing the right thing, we may get the wrong thing that we may overwrite, right? If we execute this one early, that's a write after read hazard. But it's okay if we don't need this S8 result anymore, because we don't need it anyway. Then in cycle 4, eventually we execute this AND instruction. So it takes us 1, 2, 3, 4 cycles to execute the whole program. And originally there are 1, 2, 3, 4, 5, 6 instructions, right? So we're making it run faster, but not ideal. Ideally, we want to run on only 3 cycles, 3 groups. So since here we're talking about WAR hazard, there's another type of hazard that can happen, that is WAW. What is WAW? WAW happens when there are different data paths. So for example, like you see the previous example, there are some paths doing the floating point operation. There are some paths doing integer operation. Then if we're doing integer operation, it's likely to be faster than the floating point operation. It takes fewer cycles. In this case, what is happening is this should, L2 should overwrite L1, right? In this case, L2 should overwrite L1. You can imagine there are some other instructions in between, so we're still using L1. Okay, in this case, L2 should override L1. But because there are different paths, and one path is going faster and one path is going slower, then we may end up with like the one that is issued later to be write back, to be committed earlier. In that case, this is a write after write issue, hazard, and it's a problem. So we need to address this problem. So how we can address this problem is basically by using this method called register renaming. Before that, at least you know the opportunity of reordering, right? If we detect there's no dependency, we can bring it to an earlier time. So although this OR instruction is written at a later time. So internal program order is later, but we can execute at an earlier time so that our execution result is exactly the same as if we're executing one instruction by one instruction, right? So this is reorder execution. So you may write a program, but how this program is actually executed in your hardware is unknown because your CPU may reorder the instructions in different ways. Okay, so to solve this type of WAW and WAR hazard, we need to understand the root cause. The root cause is the compiler is trying to reuse the registers. We have a very, very limited architectural register space. So in RISC-V, we only have 32 registers. So this enables us to write a super simple core that is like take a really small die size and the energy is very small energy consumption. So in this case, our program may have many registers. So our program may have many variables. In that case, we have to reuse the registers. If we're done with the variable, we can reuse the register to do something else, right? So these are architecture registers. We only have 32 of them. If we want to compile a program to follow the architecture definition, we have to reuse them. But for auto-order execution, so from the perspective of the compiler, we have to reuse S8, right? But your microarchitecture may actually have more register because you are free to design a really high-end chip, right? You can have a lot of extra registers that can be used there, right? Can stay there to be used. In that case, by doing some analysis, your hardware can figure out, okay, this S8 is not this S8, right? They're both called S8, but it's just a register reuse. So if this S8 is not that S8, then it's totally okay if we can rename it to something R0. R0 is not an architecture. It's not an architecture level register, so programmer cannot see it, right? But your hardware can see this problem and can rename it at the runtime. So what is register rename? So we rename microarchitecture register names. We rename architecture register names to microarchitecture register names, okay, to reassign these registers at the runtime. Then we can perform by hardware at runtime so that this mechanism is purely programmer transparent. So programmer doesn't really know anything. This is a pure performance optimization. That they write the same program, they don't need to do anything extra, they get free performance improvement. Okay, so register renaming, if we can register renaming, we can actually convert this program from two independent chain of instructions. So what is the one chain? One chain is this load, this add, this sub, and this end. All of them use S8, right? This is one chain. The second chain is this OR and store. We can convert from two chain of execution into three chains of execution. We know if we rename this as R0, we know load end is one chain of execution. Sub end is another chain of execution. OR and store is another chain of execution. In that case, we can actually rewrite this way, reorder it in a better way so that we have more flexibility to reorder. We can reduce a 4-cycle execution back to a 3-cycle execution, 3 groups of programs, and reduce the execution time. Okay, so this is register renaming, and still register renaming is a rather advanced technology that it actually requires a lot of extra die size and energy consumption. So it's only used in rather high-end CPUs.